Hi all, welcome to Siddha.com. Here in this video, we'll discuss about the percentage of a covalent character in ionic compounds. In our last video, we have learned that an ionic compound is formed by the transfer of electron, and when there's a transfer of electron from one atom to another atom, you get a cation and an anion. Example, we can say we have a sodium chloride. Here in the sodium chloride, sodium loses the electron and forms a cation, and chlorine gains, so it's an anion. But when you look at ionic compounds, the cation can pull the electron cloud of an anion. So that means anion is never asymmetric in an ionic compound. So the electron cloud around this anion is not a symmetrical distribution, right? It's not a spherical one. Rather, the cation, because of its positive charge, can attract the negative charge of an anion, and therefore what happens? The cation can induce some kind of a polarization in an anion, right? So if there's an electron cloud, that electron cloud will be slightly, you can say, it will be distorted, or you can say it will be polarized towards an anion. Here the electron density will be now more towards the cation here. Okay, so that means here, if you look at this cation here, it can induce some polarization in an anion, right? It is because of the positive charge of the cation that it can pull the electron cloud of an anion, and now this symmetrically looking anion will now be polarized. And we use the terms like polarizing power for the cation and the polarizability of an anion. Means polarizing power is the tendency, is the power with which this cation can attract the electron cloud of an anion. That's what we call as the polarizing power. And if this polarizing power is more, then we can say the ionic compound has some covalent character, has more covalent character. Okay, so due to this polarization, some covalent character gets induced actually in an ionic compound. So that means ionic compounds, we do not have any ionic compound with 100% ionic character, right? No ionic compound is 100% ionic. It has some 5%, 10%, 20% like that percentage of a covalent character in it. And why that is? It is just because a cation can pull the electron cloud, or you can say a cation can induce some polarization in the anion. The electron cloud will be more attracted by the cation, so therefore it will induce some kind of a polarization in it, and that's what we call as a polarizing power of the cation. At the same time, different anions get polarized to the different extent. Some of the anions, they can get induced very easily, and some with difficulty. That's called as a polarizability. That means how easily you can polarize an anion. That's called as a polarizability. So that means ionic compounds have some kind of a covalent character, and how much covalent character will be there, it depends on two factors. Number one is the polarizing power of a cation, and the second one is polarizability of an anion. Now, the factors which can explain the percentage of a covalent character in an ionic compound were actually suggested by the Fajans, right? And that's why they are known as Fajans rules. So according to these rules, it says that the percentage of a covalent character depends on the charge of a cation here, size of a cation, and the size of an ion. So let's take here an example. If you got a sodium ion and a magnesium ion, we know that sodium has +1 charge and the magnesium is +2. So higher charge of the magnesium means it will pull the electron cloud of an ion more strongly, so it will induce more polarization. So that means magnesium has Mg2+ has a higher polarizing power than the sodium positive, because the polarizing power depends on the charge of the cation. Okay, if the charge is more, it can pull the electrons very strongly. So we can say here the polarizing power depends on the charge, right? It depends on the charge of the cation. It is directly proportional to the charge of cation. If the charge of the cation increases, it will attract the electron cloud very strongly. So that means it has more covalent character then. Okay. That means if you take two examples of two salts here, you suppose you have the sodium chloride and we got a magnesium chloride, MgCl2. So we can say sodium chloride has more ionic character than magnesium chloride. Both are ionic compounds, but we can say percentage of ionic character is more in sodium chloride than the magnesium chloride, because magnesium chloride here with 2 positive charge on the magnesium can pull the electrons very strongly, and it has a little bit more covalent character than the sodium chloride. Correct? So we can say here covalent character is more in magnesium chloride than in sodium chloride, or in other words we can say the sodium chloride is more ionic than magnesium chloride. Another factor is the size of the cation. How big the size is. If you look at these two cations, beryllium and the magnesium, okay, the beryllium is smaller than the magnesium because these are the elements of the same group. First there is beryllium, then is magnesium, then after that it will be calcium. So beryllium, 2 positive charge, the charge is same here, okay, but this beryllium with small size, right? Small size here for the beryllium than the magnesium. Magnesium has a little bit bigger size, okay. The charge is the same, 2 plus 2 plus, but because of small size on the beryllium, the charge density on it will be more, and that means it can pull the electrons of anions very strongly. So that means the polarizing power of the beryllium is more than the magnesium 2 plus. So we can say here that the polarizing power again depends on what? It depends on the size, and here it is inversely proportional to the size. Correct? So we can say here that a polarizing power of the cation actually depends on the charge, and it depends on the size. And if you combine the two factors here, we can say here that the polarizing power depends actually on the charge density, because the charge density is what? It is the charge of the ion divided by the size. Okay, so here we can combine these two factors here. We can say that a cation can attract the electron clouds of an anion more strongly if the charge density is more, and the charge density depends on the charge of the ion and the size of the ion. If the charge is more, polarizing power is more. If the size is more, polarizing power is less. So that means here, if you take here the two examples of, suppose you take the beryllium chloride and we take the magnesium chloride, MgCl2. So we can say here magnesium chloride is more ionic than beryllium chloride, right? So we can say magnesium chloride is more ionic. It has more ionic character, okay, more ionic than beryllium chloride. Why? Because beryllium chloride has a stronger, it has a strong polarizing power. It can induce a little bit more, right, polarization. That means beryllium chloride has more covalent character, okay, than the magnesium chloride. You got it? So among the two, we can say MgCl2 is more ionic, and BeCl2 is more covalent. The third factor is the size of an ion, right? Size of an ion. If the size of an ion is more, you can polarize its electrons very easily, isn't it? If you have small anion and a bigger anion, right? Okay. Now you can induce, more here polarization, correct? It will be more induced here, right? Polarization will be very easily done here than with the smaller one, correct? So small size means it's difficult to polarize this anion because the electrons will be closer to the nucleus. When the size is bigger, you can induce more. So that means if you take the two examples of sodium fluoride and you take suppose the sodium chloride, okay, we can say here sodium chloride is more covalent. It has a more covalent character because you can easily induce, the polarization in anion, Cl negative there, than with F negative. The cation here is the same in both cases. Now it is a matter of anion only. So chlorine, bigger size, so you can polarize the ion more easily. So let's take here certain examples. If you look at here, the different salts here, beryllium, magnesium, calcium, anion is same in every case, and the charge here is also same, right? Beryllium, magnesium, calcium, strontium, and the barium 2 positive. But now if you look at here, from beryllium to the magnesium down the group here, these are the second group, elements, okay, and down the group the size increases. So more size of the cation means it will not polarize strongly, right? Beryllium, the smallest size here, correct? Smallest size. So when the size of the cation is small, it can polarize more. So that means if you go down the group, size increases. So polarizing power of the cation decreases here because size becomes bigger, the charge density is less. It cannot, if you go down the group, the polarizing power decreases. That means the covalent character also decreases there. Okay, so you can say if you go down the group, you can say the covalent character here, covalent character decreases. Okay, it decreases if you go down the group here. The reason is simple, that the polarizing power of the cation is decreasing down the group here. Let's take other examples here. We got the sodium, magnesium, and the aluminium. Anion is same again, but sodium is +1, magnesium is 2 positive, aluminium is 3 positive. Here the charge is increasing when you go down, here from sodium, magnesium, and aluminium, and that means when the charge, the charge increases, the polarizing power of the cation increasing. So that means when you move from sodium to magnesium and magnesium to aluminium, the charge is increasing. So that means the covalent character increases also. Okay, covalent character also increases here when you move from sodium to the magnesium and magnesium to aluminum. Hope you got the concept. Thanks for watching the video. Bye for now.